A local firm called Blackrock Energy has been interested in doing some algae experiments or algae investigation in algae for energy, and went around and created basically a consortium of other people that were interested in it, and managed to talk to Statoil Hydro, which is a Norwegian oil company, who agreed to provide funding. They were interested in also in algal energy. They have also a macroalgae project, which is basically the algae that you see that looks like seaweed. They wanted to start another project on microalgae, which is cellular and normally floats around in the water, although some of it attaches to things, and that's the ones we're targeting. And so they have these two projects going on, and and Blackrock Energy built this consortium of folks, which includes several universities besides William and Mary and VIMS, which is our sister, and their University of Arkansas, Western Michigan, and the Smithsonian Institute has had a long project that mostly focused on the environmental aspects of what we're doing. And so, of course, we were very interested because as neighbors of the Chesapeake Bay, not only do we get to investigate alternative energy, but what we're doing is very environmentally friendly. Not just the fact that algae has a neutral carbon cycle. In other words, all the CO2 that you would release from burning algae fuel has to have been sucked back in by the algae when it grows. So it's just a continuous cycle, and you're not actually releasing carbon dioxide that would normally be in the ground. So it's carbon neutral. Not only that, but particularly as it pertains to something like the Chesapeake Bay, the nutrients that the algae takes up are considered to be pollutants in the Chesapeake Bay. The nitrates and phosphates and other fertilizer type nutrients that are dumped in or run off from farming and suburban homes, etc., are things which are very bad for the ecology of the bay, and it's exactly the things that the algae likes to suck up. And then if the algae is then removed from the water, you have a net cleaning effect. So that's what led us to be very interested in the project. The consortium was put together, and we proposed to Statoil a project that we would be doing. And that started about a year ago. The actual start date, I think, was in October of last year, and then Statoil was happy with what was going on, so they funded us for another year starting in this May.
Okay. And I had read somewhere, Karl, that there's something like 100 different university research projects involving algae to fuel underway right now. Is there a sense of competition? Is it a race to some extent, or is it more collaboration?
We've not really seen that people feel like it's competitive enough that they don't want to share the story. But what we think is different about ours is that we are not focusing on a single species in a bioreactor type thing. We really are focusing on just wild algae and letting it grow, which has, of course, the minimal energy input. So if your idea is that you want to pull energy out of the water, the less you have to put in to create the other energy, the larger the net. Now, that creates some problems because wild algae, you're not absolutely sure what you're getting. And we're doing a lot of looking at how we might select specific kinds of good algae with lots of oil in it. But right now our focus is just on production and just getting as much as we can. So it's different than most of the other projects in that they're looking at specific algae or ways to grow it in a controlled environment. And of course that's much more energy intensive. In fact, the project that you're going to see today essentially uses no energy at all, electricity or anything. Now we do have a pump on this one, but it's only to replicate the tidal flows that we're going to see when we move it into its actual location. Okay. But other than that, there's no energy at all. Now the final idea will be to have mechanical harvesters, or et cetera. And so that, of course, will take energy, but really that's going to be it. Just whatever we pull up to the machine, and harvest the algae out, that's the only energy that it will take. everything else is free. The nutrients are free. They're already in the bay. The light is free. So essentially, it's minimal energy that you would need to grow something like this.
Final question, Karl, and it builds on what you were just saying. What does it take, or what would it take to get this to commercial scale, to make it technologically viable for mass production?
That's an interesting question, and we're doing some economic analysis now. The real difficulty with what we're doing is based in engineering problems. The ocean is an unforgiving environment. Large things in the ocean are prone to problems and breakage and hurricanes, etc. So it's going to be a very difficult engineering problem. We are specifically studying the scientific parts of the answer to your question. In other words, how big can it be before you need certain nutrients to be included? Does all the carbon dioxide get taken up if it's 10 acres? Does all the phosphates get taken up? Do you have to pump in new water every 100 meters? So there's some questions like that, but we don't think any of those are showstoppers. We think that there'll be minimal additions to this project. What is difficult is the idea of building something very large in an exposed environment. And so that's something really we're going to be looking at once we understand that this is possible and that scientifically and biologically we can do this. We are really not the guys to answer the engineering part of the problem. That's marine engineers and folks like Statoil that have years of experience building things in the open water. We are targeting sort of a protected environment at first, the York River, which is an estuary of the Chesapeake Bay. And so those ones are a little more forgiving. But even if you get out into the open Chesapeake Bay, you're talking about a very difficult environment. So scientifically, we think it's scalable. Engineering-wise, that's going to be a difficult problem. So that's really the answer to your question is, how big can you make something and not have it crumple up at the first hurricane?
Answer is we'll see.
Let me add one quick question. Does it make a difference, freshwater, saltwater, in terms of the growth of the algae?
What's different is that there's a completely different ecology there. And so we are targeting saline environment initially. But in fact, if you look at as I said, we have two parts to our problem. One is getting fuel and one is cleaning the environment. You can probably do a lot of very important work on the ecological side in freshwater, even if you can't grow as much algae or it's not the best algae to grow, which I'm not saying it is, but these trapped bodies of water have a lot of environmental problems. And in fact, the lake is really, it's hurting, I guess is, for lack of a better word. So even something just a few sizes larger than what we have out there would make an important benefit in a body of water like this, environmental. So I don't know, fuel-wise, environmentally, certainly the freshwater can benefit, but on a large scale, even the Chesapeake Bay could benefit significantly from what we're doing.